So I am the host of the session. I also happen to be a speaker, but I will be monitoring the chat for questions, and we, the speakers, also invite verbal questions and participation of the work along the way. And then I will try to keep us to finishing 10 or so minutes after the original time. So Marco, do you want to take it away?
Yes, sure. So thanks everyone for coming to our workshop. This is going to be a hands-on activity, and it's really going to be hands-on for this workshop. And of course, it's supposed to be hands-on in an actual classroom. So this is a joint work with Tim, Antonelli, Tova, Brown, who you just heard from, Tingxiu, Wang, and myself. All right, so first, basically, can you go to the next slide, Tim? I think you're controlling the slides, right? Basically, we're gonna split this into 3 parts. I'll give a brief introduction into the SIR model, talk about let's say a small real-world scenario, and then we'll move on to the hands-on simulation or activity with the actual Skittles, and then the third part will be parameter estimation to feed our model. Okay, so the SIR model is the model we're going to use, but as a motivation, first let me show you here a small real-world scenario, much smaller, let's say, than the pandemic. The current pandemic. This is an influenza outbreak at a boarding school, closed population, nobody's entering or leaving, and you can see on the table there, at the beginning there's 1 infected person, and then it grows from there, then goes back down. We can also see that in the graph. There's the whole thing maybe lasts about 2 weeks or so. So the question is, or the question we want to ask our students is, how can we model this mathematically? And how can we measure whether our model fits real-world data? Okay, so the model we're going to use, as I mentioned, was the SIR model. You may already be familiar with it. It's been talked about quite a lot more now with the pandemic. But just in case you don't know, SI and R stand for susceptible, infectious, and recovered. So basically, our population is going to be compartmentalized into these 3 categories, right? Somebody who's susceptible, they are not infected, but they may move into the infected compartment. At that point, they also become infectious, so they can infect other people in the susceptible population. And then after a certain amount of time from infectious, they move to recovered. Okay, and there will be some assumptions on this model. So first of all, these 3 quantities all depend on time. And our assumptions are basically at the beginning, there's no recovered population. We just started with a small population of infected people. Almost everyone else is susceptible. We assume also that recovered means basically permanent immunity. So you don't go back to being susceptible after you recovered. And you also cannot you're not infectious anymore at that point. Like I mentioned, the community is closed. So this means that at all times, the sum of these 3 quantities, S plus I plus R, remains constant. We also assume recovered means really recovered, not nobody dies from the disease at this point. Okay, and then comes the fun part, basically, or the difficult part. We would like to ask our students, how can we model these quantities based on basic knowledge of infectious diseases and how they spread, right? So, so if we start with the susceptible population, we might think, you might want to give your students ample time to think about this, maybe by themselves or in groups, but we might say, okay, the susceptible population, most of the population is susceptible at the beginning. At that point, some of them will begin to become infected, so that will decrease over time. And how is it going to decrease? Well, if there's a lot of infected people, then there will be a lot more infections or transmissions happening. Also, if there's a large susceptible population, a large number will become infected. So seems like S prime might depend on both S and I. This discussion will take a much longer period of time in an actual classroom. But eventually you might come up with some model for S prime. So for example, as I mentioned, it should make sense more or less that S prime should increase as if S is large or if I is large. So of course, there's many reasonable equations that one might propose that adhere to these dynamics. But maybe one of the simplest ones is simply saying S prime is proportional to the product of both S and I, right? And we assume A is just a parameter that we'll try to estimate later, positive number, so we'll put in a negative sign in front because we expect S prime to decrease over time. And then, okay, similar exercise with R prime. You might even want to begin with R prime because it might be a little easier to think about this variable actually. And so people who, to become recovered, first you have to be infected, right? So people move from the infected compartment to the recovered compartment. So it should make sense that the rate of change of the recovered population is going to be proportional to I. Or it should be big if I is big. Again, there might be different reasonable models, but maybe the simplest one is this proportionality of R prime being directly proportional to I. So we come up with this equation. And then what's left is the infected population. We don't have, at this point, we don't have to think too hard about this one because we can use our assumption that S plus I plus R is constant, right? So we can solve for I prime in terms of S prime and R prime. And since we already thought about S prime and R prime, we can simply write down what I prime is. In this case, A times S times I minus BI. Those two terms are the two expressions we came up with before, right? So to summarize, our model will basically be this system of three equations and three unknowns, a system of differential equations. It's a nonlinear system, but still simple enough that we can analyze it, etc. So it says my connection is unstable. I hope you can hear me okay. But that's basically in sort of a summary of how to come up with this model. And this is the model we're going to use or think about for the rest of the activity.
So now there's a lovely semioid scenario which goes through the real world scenario of the English boarding school outbreak and the development of the SIR model. And as part of the Mindy workshop last summer run by Semio to introduce teachers of differential equations to a modeling first approach, we as participants in that workshop, we came up with this idea of modeling an outbreak in the SIR model using Skittles because we were provided with a huge quantity of Skittles for a hands-on opportunity in the workshop. So we have all these Skittles, and we're going to walk you through something that you could help your students. It's already hands-on to think about the assumptions of the model and do the numerical ending of the project. But this provides an additional way for each student to generate their own data of an epidemic and to see the trends of how different epidemics with different randomness will still exhibit the same overall behavior. And so we cooked up a simulation of a school with only 40 students because no one wants to be counting and 700 some Skittles, right? So take a smaller size population for this exercise, So we're going to have a population of 40 students. And in order to represent the different states that these 40 students can be in, you're going to need 40 times 3 Skittles. So we have 40 Skittles of one color, 40 Skittles of a second color, and 40 Skittles of a third color. We chose yellow, green, and purple. And so any one student can be represented by 3 different Skittles at different points in time, depending upon their status. Are they susceptible? They have not yet been exposed to this new flu. Are they currently infected, or have they already been infected and now they've transitioned to the recovered category? So the school will begin all yellow with all susceptible individuals, and someone gets infected and becomes replaced by a green Skittle. So now you have 39 yellow Skittles and 1 green, and like, we got to figure out what happens. So in an ideal world where you're sitting with your students in a classroom and they all have Skittles in hand, each student or each group of students could have their pile of 120 Skittles and a cup for mixing them in, and then a copy of the instruction sheet, which is linked here in the slides. I know you can't click on it through Zoom, so we're going to share links as needed in the Zoom chat. But there's an instruction sheet that will walk the students through the same thing that we're going to be walking through. And then, they would be hands-on doing this process. And I think it would be helpful to work the whole group through a few days of the simulation before turning students loose with the instructions. And what we're going to do today, because we don't all have Skittles in hand, this is virtually hands-on. We did the Skittle tossing already, and we have some experimental data. And so now we, the workshop participants, are going to break down into different data sets, like everyone working with their own, not completely unique. We have 3 different experimental data sets that you can choose to work with. And we're going to walk through the simulation, pretending that the Skittles have been tossed, looking at the results and figuring out, how do we understand the SIR model and the transition of individuals from susceptible to infected to recovered, and the collections of the SI and R portions of the population. So Tim is throwing these links in the instruction, or these links in the Zoom chat. And so I would encourage you to open up in particular the link of experimental data, and that's a spreadsheet. And please download the spreadsheet to your device. That way everyone isn't trying to edit the same copy online. So download the spreadsheet so that you can edit it. And if you can, exit the full screen nature of Zoom so that you can split your screen half Zoom and half your local copy of the spreadsheet. So you're setting up Zoom so that you can see our shared slides and the portion that we're all walking through together, and half on the spreadsheet so that you can be editing it as we go and seeing your own data, your own epidemic take shape. Within that spreadsheet, there are 4 tabs that you might want to choose. Data 1, data 2, and data 3 are just the results of 3 different Skittle toss simulations that we did. We tossed, I have my Skittles here. And then Sim Your Own is a randomly generated through Excel. Everyone will get their own actually unique data. So data 1, 2, and 3 are a bit simpler. There's instructions on Sim Your Own on that tab that you can, choose one of them, choose your own adventure. Okay.
I just realized I actually never tested if you can download it in Excel and then it still works. So that'll really be an adventure to see if that works. It works in Sheets, but I don't think you have edit access in the Sheets. So if that doesn't work, maybe we could consider just adding edit access to people that you still have to kind of, or maybe you could copy and paste it into a sheet.
You can make a copy.
Yeah, I've only done it in Sheets, so yeah.
Okay, I would assume that those formulas go through, but yes.
Kind of would too.
Let us know in the chat if you're having issues, or just speak up. There's only 13 of us here, so just speak up. That's probably even better. But chat if you're more comfortable that way. Let us know if you need more time to get set up, or if you have if you're having technical difficulties. How are we doing? Could we proceed talking about the first day of the epidemic? Okay, I'm going to go ahead. Okay, so there's some novel flu virus, right? They're constantly mutating. So here's one that no one has immunity to, and in this population of 40 students at the school, someone comes sick. And so the population that we're going to be working with is 39 yellow Skittles and 1 green Skittle, representing 39 susceptible students, 1 infected student. And no one has yet had time to recover, so there are no purple Skittles. And so students will put this collection of Skittles into their cup and shake it up. And then we have to figure out what to do next. So Tim is going to explain the sampling here.
Yeah, so it's a bit, it's a lot, but we're gonna kind of break it down. So the first day, right after the 1 infected student comes back to school, they then, we assume, spread it to other people. And so we have to make a couple assumptions here. And we just try to keep it simple with this simulation. So we're gonna assume that each infected student has 2 close contacts per day. So pretty much each day in the cup, we're kind of mixing it up and then drawing 2 times the number of infected students. And we're gonna keep track of this in a table, right? How many infecteds there are determines how many of these we draw for potential transmission events. We'll then assume that we infect all of the susceptibles that we draw. And initially, it's very likely that, okay, you're only gonna draw 2 because there's only 1 infected. It's very likely you'll draw 2 susceptibles. And so you'll end up with 2 infecteds for the next day. So we have these 2 events kind of going on each day. The first is that transmission. And we found sort of the best way to keep track, if you look over on the right, is to sort of break up the days where you also have, okay, I new and R new. So at the point where you draw the 2 susceptibles, 2 times I, you would say, okay, my I new is going to be 2 because I've converted 2 yellows into greens. And at the end of the day, it's probably best if you sort of wait, figure out the numbers first, and then convert them. You can just eat the yellow Skittles and replace them with green because they never go backward. You'll never need those 2 yellow Skittles again. So that's the transmission event. And we're going to go through a couple days as much as we have time for. So if people do have questions, please do jump in. It's where it starts to get kind of complicated. That PDF link, the second link in the chat, also goes through it in a bit more detail if you need to sort of fill in any gaps. And of course, that will be available for reference too. If you do decide to adopt it in a class and you're like, wait, what was that, day 1 thing again? That should all be in there. So after the transmission event, you also need to account for recovery. So we have some sort of rate of recovery. And again, to keep it simple, we're just going to assume that the recovery period is on average about 2 days. So what that means is you should expect about half of the infected students to also recover each day. And so we're going to take half of the current number of I and then just round whatever we get, and that will be our R new. So just to sort of walk through these numbers, of course, we start with the 1 infected and 39 susceptible. We draw 2 because it's 2 times I. In this case, and you might get something different, you might get lucky and get 1 infected in there already. So you might have 1 new infection, but probably you'll get 2. Then we have to account for, okay, that 1 infected recovers because half recover, and we're going to round 0.5 up so that we do get a recovery. And so that means the net number of infections is actually I new minus R new. So we actually only net 1 new infection. At the end, we're going to have 2 infecteds and we're going to have 1 recovered. So we just sort of represent that in the population, and a quick check at the end of each day is the total should always still be 40, right? Again, it's a closed community, as Marcus said, so no one's entering or leaving. So just double check that the numbers add up, and we have 1 recovered here, and then we have the 2 infected and 37 susceptible. So whether you're drawing it or you're just following along with one of the pre-made data sets, I think Tingxiu is going to walk through in a little more detail the entering of that in the spreadsheet, and you can actually sort of track your epidemic as you go.
So here you see the spreadsheet, and just now we started with day 0. So in day 0, initially there were 39 students susceptible, and then 1 infected and 0 recover. Just now Tim explained that, and so assuming each infected student will infect 2 new students. So therefore, in day 2, so the number infected will become, there are 2 new infected students. But however, and there would be one recover period is 2. So assuming half of students will recover. So that means, and so day 1, if you take 1 divided by 2, that is 0.5, we round it to 1 recover. So therefore in day 2, and in the spreadsheet, and you see I is 2, and then that means, susceptible will drop from 39 to 37. So then in day 1, and you have 37 susceptible, and then you have 2 infected, and you have 1 recover. So total is 40, and that is day 1. And let's move to next one.
Can I check in quick before we go to day 2? Check in the chat.
Yeah, go ahead.
Those of you who chose data 2, the data 2 tab, so you're doing experiment 2. How many people do we have doing that? Hopefully we've got a couple. If you're doing experiment 2 on day 1, how many susceptible people did you end up with? Type it in the chat. Do you have anybody doing that? Number of susceptible on day 2. Sorry, on day 1. I mean on day 1. Experiment 2, day 1. That we just finished calculating. Maybe no one is doing this experiment. If you're on experiment 1 or experiment 3, your numbers for day 1 were exactly the same as our demo. If you were doing if you're doing experiment 2, then on day 1, you actually drew 1 green and 1 yellow Skittle. And so you have 38 susceptible, 1 infected, and 1 recovered. So it looks like no one is on that data set. So that's too bad, but that's okay. Okay, day 2.
So go ahead.
Yep. So under the assumption that each student, has like 2 close contacts per day, may already have immunity or who may not, we're going to draw 2 new Skittles from the population per currently infected student. So on day 1, we finished with 2 infected students. That means we need to draw 2 times 2. We need to draw 4 Skittles to represent the 4 close contacts who had the potential of becoming infected. And in this case, in my experiment, I drew, again, 4 yellows, and the likelihood is high right now, but okay. So I drew 4 susceptible students. That means that half of, let's see, so then those 4 susceptible students will all become infected, right? That's what that means. Your students working with actual Skittles in the classroom can now eat 4 yellow Skittles and dig out 4 green Skittles from where they've been waiting in the wings. And the 4 green Skittles enter the simulation, representing that 4 students have transitioned from susceptible to infected. Yes, that is correct, Brody. Yep, data sheet 2 would have 38 susceptible people on day 1. Yeah, so now we have some of the people who were infected on the previous day are recovering, and it should be about half of them, and we round to the closest whole number. So on day 1, there had been 2 infected people. If we take half of that, that means that 1 person is recovering. So our new, that's the number of people who on day 2 have newly recovered, is half of the infected population on the previous day. And that means that the total number of recovered people on day 2 is the old number of recovered people plus those who are newly recovered. And so we have 1 from R on day 1 and 1 from R2, R new on day 2. And that makes 2 recovered people by the end of day 2 of our epidemic. And so we have 2 purple Skittles, we have 5 green Skittles and 33 yellow Skittles still. And that represents that 33 students are still susceptible. 5 are currently infected and 2 now have immunity. They will not become infected again. These 40 Skittles pictured are the ones that go into the cup to shake and to draw again. But now now it's time for each of you to calculate your day 2 data. So Tingxiu, do you want to take that again?
So, and just now Tova already explained how to get day 2. And let me just, repeat it again. So, and if you look at, day 1, and to calculate day 2, you will look at day 1. So under day 1 and infected people now is 2. So, and because half of them will, the recovering period is 2. So assuming half of them, in next day, half of them will recover. So if you take a 2 divided by 2, then you have 1 new recover. So plus the previous one recovered. So total, and in day 2, 2 students recovered. So then in day 2 under R, and it's 2. And then also, the number of new infected is 2 times. So when 2 times 2, you get 4. And because 1 recover, another 1 stays, so total would be 5. So therefore, under day 2, and number of infected would be 5. So therefore, then susceptible students drop from 37 to 33, because 4 new infected students come up. So that's why, and the susceptible becomes 33. So that's the number you can see from day 2. And correspondingly, if you look at below the graph and the spreadsheet, plot day 2 automatically simultaneously. So you see the plots under that and that for day 1, day 2 as well. So that is about day 2. And if you do it on your own spreadsheet, and that hope you can do that correspondingly. So that's day 2. We can move on day 3.
Yeah, let's move on to day 3. Can I check in with those who are working on sheet 3? If you're working on experiment 3, how many susceptible people do you have at the end of day 2? It's different from the data we've been showing in our demo. Anybody working on experiment 3? So here are the numbers for data for experiment 3. There are 34 susceptible at the end, 4 infected, and 2 recovered. So if there are 4 infected individuals, how many Skittles would you draw on the next draw from 4 infected individuals? Assuming each one has 2 close contacts, we would draw 8 Skittles and see what happens. How many of them are yellow, green versus purple? Okay, so in our demo, we had 5 infected individuals at the end of day 2. And so we need 5 times 2, we need to draw 10 Skittles. And out of the 10 Skittles, immunity is starting to help already, this epidemic. In the demo experiment, we drew 2 recovered students who already have immunity, and then we drew 8 susceptible students. That means the infection starting to take off, right? In addition to the 5 people who were infected the day before, we have 8 new infections, and okay, half of the 5 people recovered. And if we round up again, then that means that 3 of them recovered. So our new number of infected people, we have to take the old number of infected, that's 5, add in the new number of infected, that's 8, and subtract off the number of new recoveries, 3. So we have 13 minus 3, 10 new infections. Yeah, it's growing quickly. Okay, Tingxiu, walk through our calculations.
Tova explained. So, and if you look at the spreadsheet, so, and you get 10 new infected, and also among the previous, in day 2, there were 5 and 3 recovered. So that, 5 divided by 2, there would be 3. 3 recovered plus day 2, there were 2. So total, there are 5 recovered. So that's how you get 5 in day 3. And then that's how you get 10 new infected in day 3. So then sorry, and I did to, okay. Actually, there was a, so that would be, Tova, do you see?
Sorry.
Okay.
What's the question?
So about day 3.
Oops, I went back. Sorry, my mouse is very sensitive. Anytime I like touch it, it scrolls. I'm like, I think we were on day 3. Sorry, that might have been my fault.
There we go. Okay.
So, yeah. So in day 3, and if you take 5 times 2, that would be 10. But in day 2, and 3 students recovered. So plus previous 2 students, so total that would be 5 students recovered. So that will be day 3.
Yeah, so it's tricky. So you have all these sort of different ways. I don't know. I find it easiest to maybe sort of take I new and R new and then just take that difference, and that's your net number of new infections. But yeah, this is something we struggle with. It's kind of even though it is somewhat simple, it is nonlinear, and you have sort of things coming in and going out at the same time. And we're really discretizing a continuous time model.
Yeah, so if you look at
tricky.
Sorry, that's tricky.
Go ahead.
So yeah, so if you look at the I new, and it was 4 in day 2, so 4 times 2, that would be 8, and so you get 8 new infected. However, if you look at day 2, you originally have 5 infected, then 3 recover, you still have 2, remain infected from day 2, and plus 8 new infected. So total would be 10 infected in day 3. And then correspondingly, when you have 8 new infected, then the number of susceptible drop from 33 by -8, you get 25. That's how it gets. So that will be day 3, and then correspondingly, you'll see the graph below, and then it's time to look at day 4.
Yeah, and so we wanted to at least get to day 4, and then I don't know what the timing is. Are we going to like 2:25? Is that right? And again, if people need to leave and they want to follow up with us later, of course, feel free to do that. But yeah, so it gets even more complicated. So as you might have guessed, yes, it starts to take off exponentially. It does eventually slow down because you start, also drawing the infecteds and the recovereds, and they cannot become infected. But before it does that, it's possible you might have to draw like half of the Skittles or even more than 40 of the Skittles. So we had to somehow account for this. And what we decided was to have this sort of like second way to do transmission if the number of infecteds reaches this threshold of 10. And by the time you get to 5 infected, so that, you would be drawing 10 close contacts. So when you get to 5 or more, what we decided was to just draw a sample. So we're only ever going to draw at most 10 Skittles from the cup. And that simplifies the counting and stuff, even if it makes the calculation a bit more complicated. But the idea is this sample represents sort of the relative frequency of susceptible students that each infected would encounter. It's sort of like the successive transmission of each of their encounters. So the fact that we drew 10 and 6 of them were susceptible means there's like a 60% transmission rate per infected student. So instead, what we switched to now is sort of calculating that relative frequency. So here we get 60%, and we're going to multiply that by the number of close contacts. So 2 times the number of infecteds on day 3. And for this one, we got exactly 12. Sometimes we'll have to round that. So here we get 12 new infections. And of course, that now sort of follows what we have been doing. The 12 new is going to go here. We're going to add that, but subtract the new recovered, which is half of the infecteds. So we net 7 new infections, and we also get 5 that go from I to R. All right, so this is kind of the snapshot, and things start to happen very quickly now. We're kind of at the peak of the epidemic. So this is our snapshot of our Skittles, and we're eating a lot of yellow ones at this point. And so day 4, I don't know if we want to go through or at what point we might want to just sort of let people do as much as they want to do. And then we can talk a bit about what you can do at the end with like parameter estimation. But maybe let's go through at least one more of these, I guess.
Yeah, I think finish day 4 and then we maybe should transition. We can look at the summary slide and then move along.
And then if people have questions or issues, we can just open it up.
Mm-hmm.
So I think, yeah, I don't know, Tingxiu, if you also want to go through this, I mean, maybe we get the pattern at this point. The main thing that we changed was just how are we getting this 12, because we don't want to draw 20 Skittles.
Right.
So we start to run into issues with sampling without replacement, where maybe they're not going to be accurate anyway.
Right.
So we use this approximation.
Yeah, so that's why, and we, use just now the previous slide and mention that, and use the relative frequency to calculate that, and because it would be too many to withdraw. On the other hand, is that when you have more students infected, and then based on previous assumption, 2 times each infected student, infects 2 new students. And if you base on this, then eventually you will not have enough susceptible to be infected. So, and that is when it gets more, days, then it will be good to, consider some use frequency, relative frequency to calculate number of infected as well. So from day 4, and we switch to and multiply by, the relative frequency of suspected students. And in that way, and modeling can be a little more accurate.
Yeah, and that brings up a good point, I think. So this sort of follows the same as day 4. We're doing the relative frequency, and that we can see goes way down. So it's 30% now. And then we just extrapolate by multiplying by the number of close contacts. In this case, we round and get 2 new infections. So now our number of new infections is going down. Although we have 11 here, so maybe I rounded that wrong. Maybe we rounded differently at different times. But anyway, you get some number of new infections, and then you just sort of proceed. Now, at this point, you do sort of have to be careful. You always kind of want to check the new predicted number of infections against your susceptible pool. So at some point, you'll probably get some predicted number of new infections, and I'm just kind of sort of speed up, and that way, if people have questions, we can go from there. But if your predicted number of new infections is, greater than the susceptible pool that's remaining, you would just say, okay, everyone has now been infected at this point. And then you're just sort of waiting for people to recover. So you have like a geometric, roughly half recover each day at the tail end of the epidemic.
So this switch somehow it is also similar to what we talk about in differential equation class, the logistic model, right? So, and at the end, when the infected people get more and more, and then the actually rate of infected could be a little bit slowed down. That's why it would be more reasonable to multiply by a relative frequency.
So let's see, I think at this point, everyone's sort of been infected, and you just have half recovering. So you're eating all the yellow ones, and now you're eating half of the green ones each time. And eventually you don't really even need to simulate this. You can just leave the Skittles out, and each day in your table, you're just sort of recording half and waiting for everyone to recover. So, I mean, if I may, I'll just sort of kind of show what you can get. So each person will get something slightly different when you're actually doing it with Skittles, but roughly the same sort of behavior. And even though we've discretized what's really a continuous time model, we get similar dynamics here. So each student can sort of generate their own trajectory of the epidemic, and can sort of talk about the differences among them just based on randomness and kind of stochasticity in the population. And so what's kind of nice is there's a lot of different directions you can go with this after they generate their own data, or if you want to just tie it back to the boarding school data, which I think that pre-existing module is based on that data. So you can compare those two. We actually tried to make the parameters, the idea that you're drawing 2 times the number of infecteds and the average recovery period of 2, we tried to pick those to kind of match that data set. So you get similar looking trajectories. Of course, we didn't do 700, but you could scale that. You could scale that up and see what you would predict in that case. So, one nice thing we thought you could do is just try to actually estimate these parameters based on your simulation and even sort of compare what people get for their parameter estimates. And if you go into the details, you can get things like the basic reproductive number, the R naught, from these parameter values. And the way we figured to do this is you can approximate the solution to the system using Euler's method as a quick sort of simple way to do it in Excel or in Sheets. You do sort of need to be careful with your delta T. So how finely you do that, the numerics, we found like a delta T of about 0.1 should work. And you'll get this sort of numerical solution. And just put this up. This is actually the last slide, and then we can open it up. But this is what I got for, I did one of the iSim ones. So I think, oh no, this was based on the one that Tova did. So the actual numbers that we went through. If you sort of compare those values in the infected row, and then down here, I just sort of made a vector of time, which is going up by 0.1. And I'm just iterating Euler's method here for the S and I starting at 39 and 1. And if you do it in Excel, you can use Solver to really sort of fine tune and zero in on these best fit parameters. I just sort of made a residual squared row and looked at the sum of residuals, and just by sort of going back and forth and finagling that, I got it down to what looked like decent parameters. And you can sort of compare. So really, you can open this up and have students try and fit it. And we thought it was kind of cool because it's their own unique data that they can actually generate. So I know that we're getting close to the end here. So I guess since I'm already talking, or Tova, if you want to wrap it up, since you're kind of the host, want to take it away?
Okay, sure. Yeah, so we would like to thank the organizers of the Simiode Practitioners Workshop that ran last summer. That was an excellent workshop and an introduction for us to this modeling first approach to differential equations and to the Simiode community. And we would highly recommend getting involved in workshops like that in the future. Lots of opportunities can open up and lots of cool things to do with your students. We've linked here the modeling scenario published by Simiode was the inspiration for our contribution here. This introduces the SIR model and that real world data and provides like the perfect starting place to dive into this with your students. And then whether you want to use the real world data and add this hands-on extension using the Skittles simulation, we've written that to kind of pair in with the pre-existing scenario and be an optional extension of it. And so we link here as well our early draft of that, of the instructions. And so thank you to all of you who have participated with us today. I hope this has been interesting. Are there questions? Are there comments, ideas? Anything? I'll open up the floor.
I have a question.
Yeah.
One part that was sort of confusing me, and maybe it's because we're trying to simulate what you would do in the classroom with Skittles with the virtual setup, which was really well done, by the way. Thank you. It's fun to use. But I was kind of confused at the part when we got to around day 5 as to why are we taking a sample? What is it that's making it too cumbersome to do it the other way? I think I'm just slightly missing the point.
You wouldn't have to. You could keep drawing Skittles, but for example, I think we had one day with 17 infected people. So you have 40 Skittles in your cup. You need to draw 17 times 2. You're drawing 34 of those Skittles. You can certainly do that. That's fine. It just gets cumbersome.
Tedious. Okay, that's what I was thinking.
The method was a way to reduce the amount of hands-on computation you have to do. But depending on your class, maybe you don't want to go into that kind of statistical. You could draw n-I Skittles. So if you leave out all the infected, n-2i, oh, and see like the complement, that's it. Yeah. So there are multiple ways that you could maybe get around this, but
it's tricky. I'd be curious. I don't really know. I guess sort of assumed you would start to run into issues with the fact that we're actually drawing without replacement. So for example, you start to draw themselves, like you're assuming each student is meeting with 2 other people. But then you draw a whole bunch, you're kind of drawing the same infecteds that are the ones going out. So they're kind of interacting with themselves. I just felt like there was something to do with replacement, without replacement. But I don't know. I would be curious to see if that changed the result. You could certainly do it that way up until the point where Tova mentioned if you have to draw more than you have in the, well, 34 wouldn't do it, but you could potentially get, 22 infecteds on the peak, and you can't draw 44. So you need some way to account for it. Maybe you just draw all of them at that point, or what Brody mentioned. So definitely you can amend this in different ways.
Mm-hmm.
Thank you.
Yeah.
I was curious if you've ever had a student do the simulation and end up with susceptible students at the end.
Yes. Data set 2. 2? No, 3.
Not 2. I finished 2. It didn't do
Yeah,
that.
you finished 2. It's 3 that ends up with 1 susceptible left at the end of the infection. So it happened to us once so far.
Okay. Thanks.
Yeah. Yep.
Yeah, we should clarify, we developed this for a summer workshop where we've demoed it a couple times, but we actually, at least I haven't since then been able to use it in a classroom. So we're still sort of tweaking it. So yeah, this is all really great feedback. And I would just be curious, just based on the stochastic nature of it, what kind of weird stuff you might get sometimes.
Mm-hmm.
Could you also simulate this using dice maybe to avoid some of the Skittle issues? You could just give them the Skittles to eat while they roll the dice.
Actually, that's a great idea. Yeah. Then you actually have 3 sides. You probably only need 4, or you could divide by 2, right? Or something
Or you
like
could
that.
use like role-playing dice where you have percentages and you have 20-sided die and things like that. So you could do other things.
Yeah.
That's a great idea. Yeah.
That'd be cool.
I think we used Skittles because we had a giant, well, for this workshop, we were sent like a bunch of things, and one of them was a giant thing of Skittles. And we thought, what can we do with this?
Yeah,
It's an excuse to
I
eat
was
a lot
in
of Skittles.
the other workshop and I got the same
Cool.
pack of M&Ms.
Right.
My M&Ms did not last long enough for this.
No,
for
room
workshop.
3 was in the same workshop, and they had M&Ms. So whatever they're talking about also has M&Ms in it. Yeah.
That's right.
Okay, so I think, I don't know if we can just hang out, or let's see, I have something else, but let's see what's going on. At 2:45, I have something, so I'm happy to hang out, or just, when should we end the Zoom and just wander around our Sakoko world?
Yeah, we got one more question coming in the chat, so maybe.
Sorry.
And then, we can hang out in the room for a little bit in case anyone else, has more questions or wants to discuss. Otherwise, it's also nice to have a break between conference sessions. So, okay, so the question was, how much time does it take for your students to complete the work? And that is a very good question, because we have not demoed it in our classes yet. With like running through this ourselves and forcing some colleagues to help, I think a very quick explanation of SIR model and the rules for the simulation plus doing the simulation took in one trial about 45 minutes. And so that's maybe about a class period. But before that, with students, you would certainly want to take time to go through the derivation of the SIR model, and so that they understand better a basis for where this is coming from. So this could be a 2 or 3 days of class, or it could be something that you work into one day of class, introducing it, and then a project for them to take home and do their own Skittle simulation with the instructions. So we don't really have a good answer to that question yet. It could be used flexibly, I think, but okay. All right, thanks to you all. Have a good rest.
Thank you all.
And we'll see you around the conference or in the
lounge, one of the lounges. I see people just hanging out in the lounge.
Right?
Yeah. We could join them. They look very lonely.
Yeah.
Great.
All right.
Thanks.